In this chapter, we're going to talk about organic compounds that have oxygen in them. And we're going to focus on oxygen when it has single bonds to the elements that it's bonded to, and not double bonds will be chapter 15. The overview for this section is we're going to kind of get an overview of organic compound functional groups. We're going to talk about nomenclature and classification for different types of alcohols, the physical properties, and then the reactions that they undergo. We're going to talk about some specific types of alcohols in different formats, so glycols and glycerol. And we're going to get into phenols and what those are in terms of different types of alcohol groups. And then get into other types of aldehydes and ketones. These are actually doubly bonded oxygens and some of the properties. And then talk about sulfur compounds, which are a lot of times analogous. They act in a similar way to alcohol, but we'll talk about those differences as well in this chapter. In previous chapters, we've spoken about carbon-based compounds, hydrocarbons that just have carbon and hydrogen associated with them. And if they're single bonds, we don't consider those to be functional groups. Now we're going to get into functional groups that contain oxygen, and we're going to be talking about what types of chemical reactions those can undergo. Typically, what we're looking at when we look at functional groups, specifically when we have some other element that's not hydrogen or carbon, we're going to have something that's going to be pulling electrons towards it more. So anytime we have oxygen, nitrogen, sulfur in here, because of the electronegativity differences between these atoms and the carbon that they're attached to, they're going to pull electrons towards themselves and away from the carbon. And this creates this dipole moment, so this change in the relative amounts of where electrons are and where protons are. And it allows for this then to set up processes for chemical reaction. Just like when we talked about double bonded carbons, these are heavy, they have a lot of electron density in there, and they can chemically react and use those doubly bonded electrons to interact with other things. These lone pair of electrons now are poised to interact with other things because they have partial negative charges. And this carbon is a site for an attack by electrons because it's partially positively charged. So when we talk about, it's just a term that you may see, heteroatoms are atoms that are other than carbon or hydrogen associated with them within the carbon backbone. Some terminology that we'll use to identify different parts or different groups within the chain are, sometimes we'll use the terminology of a primary, secondary, or tertiary or quaternary carbon. Here you can see that there's a difference between this first carbon if what is not being shown here right now are the hydrogen atoms that are attached. And if the carbon of interest that we're looking at is attached to one other carbon, we consider that a primary carbon. If a carbon of interest is attached to two other carbons, that is going to be a secondary carbon. Now here, those are actually hydrogens. So all of these spots are actually, that don't have the hydrogen, these are actually hydrogens, not carbons. So this third one, we can see carbon, and we have three different carbons attached. So that carbon right in the middle is a tertiary carbon, and then of course the last one attached to four carbons is a quaternary carbon. And you can see on the right we have a skeletal structure where we have a carbon on the end, and that's the primary carbon. So that would look just like that one shown in the image here. A secondary carbon is shown here, where again, when we're doing skeletal structures, we're not showing any of the hydrogens that are attached. This is a tertiary, and this is an example of a quaternary carbon drawn out in the skeletal form. What we also want to know is that sometimes we'll refer to different hydrogens. Now the hydrogen, since it's always going to be attached to something, we're going to refer to the hydrogen value, so that primary hydrogen is actually attached to a carbon that's just attached to one other carbon. So on this compound, this is going to be with the primary carbon, there are primary hydrogens attached to that. And if we look at this other element, The secondary carbon here is attached to secondary hydrogens. So the hydrogens are associated with the carbon that's attached again. And then here we have a tertiary carbon, and this hydrogen is a tertiary hydrogen. The question is now, can we have quaternary hydrogens? What do you think about this? If we have a carbon attached to 4 different carbons, there's no room for hydrogens to bond, so we wouldn't have a quaternary hydrogen. So I'd like you to take a look at these 2 skeletal structures, and I would like you to classify the carbons on those and also to classify the hydrogen atoms after that. So pause. I'm going to go through the answer, but I'd like you to try this on your own first, and then we can chat about the answer and how I solved this. Okay, for this problem, what I do is I first identify all of my primary carbons. So those are the carbons on the outside that are only attached to another one. So in red here, I've identified all the primary carbons, and we know that those primary carbons, on those are going to be primary hydrogens. So all of these hydrogens that are attached, there'll be 3 of those for each primary carbon. Remember, that gives us our 4 bonded things, and these are all of the primary hydrogens. So the primary carbons here, and all of the outside hydrogens are primary. Now if I look at some of the other elements in here, I have this carbon as well, and I can see it's attached to 1, 2, 3, 4 different things. So this is a quaternary carbon. And this one also, 1, 2, 3, and 4, that one's also a quaternary carbon. So we also now have, we can't connect it to any hydrogens. It's already has its octet, so those are complete. Now if I look at the same thing with the other element, I have 1, 2, 3 primary carbons on the outside. Each of those hydrogens that's attached to it are going to also be primary hydrogens. And then the carbon in red. We can also identify then, I'll look at some of these other spots. So here, this carbon at this center is attached to 1, 2, 3, 4 carbons. So this is a quaternary carbon, and it can't attach to any hydrogens because it's already got 4 attachments. This carbon here has 1, 2, 3, so this is a tertiary carbon. That means it also has to have 1 other hydrogen attached to it. And that hydrogen will be a tertiary hydrogen because it's attached to a tertiary carbon. And now looking at the other positions, these are all a little different than the other ones. These positions are going to be attached to other carbons at each location around this ring. And that means that these are all secondary carbons, and the hydrogens attached to them are also going to be secondary hydrogens. And remember, we need to have those 4 attachment points, so each one of those, there'll be 2 hydrogens on each one of those carbons. So secondary carbons and secondary hydrogens. So that's the answer to this question. Hopefully you were able to walk through that or figure that out before I was able to walk through it. So remember this periodic table trick where I usually move hydrogen over here. We're really in organic chemistry and biochemistry, really looking at this part. And remember, we can draw those diagonal lines down the rows of the periodic table, starting with fluorine, and we can generate this kind of electronegativity grid where anytime we have to jump over different lines, that's going to be a difference in electronegativity. And we know that most of the things we're looking at, especially in this chapter, is oxygen. And that means that it's going to be more electronegative than carbon by a couple of those lines, which is a pretty significant difference. So we can see here we have typically partially negative charges towards when we are talking about connecting to an oxygen, for example, and then that means we're going to have partial positive on the carbon. So this is the basis for the chemical reactivity and the behaviors and properties that we're going to see in the next few slides here. So here are a list of a few different functional groups that have just single bonds associated with them. We're going to focus on alcohol groups, and the basis for this is basically a carbon chain. So anytime you see an R in organic chemistry, that just means a chain of carbons of an indeterminate size. And attached to that chain is an oxygen and a hydrogen. And so this is an example of a methanol. And typically these groups that we are talking about, if we're talking about a group, typically we'll call that group name a hydroxy group. But the compound that it's attached to will be defined as an alcohol. Here's an ether where there's an oxygen in the middle of a chain, and we call that an alkoxy group. There's other things that we'll talk about maybe later in terms of other functional groups. Halides that have halogens associated with them. We'll talk about amines with nitrogen-based compounds. And we'll also talk about thiols and potentially sulfides as well in this chapter. So a couple of other different types of functional groups. Just like when we were classifying hydrogens on the carbons, these different groups that are attached are going to define if something is a primary, secondary, or tertiary group. So I have actually two different examples here. A lot of times when we have an X, that is actually a kind of way that we define halogen, or the chlorine, bromine, iodine, different types of groups. And so this is the same way that we also look at alcohol. So I know we're focusing on alcohols in this chapter. And if we're looking at this carbon, for example, that's attached to our halogen, this is going to be a primary halogen because we are attached to a primary carbon. It's also going to be a primary alcohol. So the same way, the functional group, we're looking at what the attachment point is with the carbon to determine if it's a primary, secondary, or tertiary. So again, for this second one, this carbon is attached to two carbons. That means it's a secondary carbon, which means it's a secondary alkyl halide or alcohol. The third example is it's a tertiary carbon because it's attached to three other carbons, which means that this group is either a tertiary alkyl halide or a tertiary alcohol. Down below you can just see the skeletal form of examples of this. Again, looking at the carbon it's attached to, we have two carbons. This is a secondary carbon, so we have a secondary chloride that's a halogen, right? Here we have 1, 2, 3, so it's a tertiary carbon, which means it's a tertiary alcohol. And finally on the end here we just have one other carbon it's attached to, so it's a primary carbon, which means that the hydroxy group attached to it makes that a primary alcohol. So here I'd like you to classify each of these as an alkyl halide, as a primary, secondary, or tertiary alkyl halide, or a primary, secondary, or tertiary alcohol. So post your answers for A, B, C, and D in our Blackboard space. So some of the things that are going to determine the properties of these different functional groups and the different compounds that they are on in terms of boiling point and melting point and interaction and solubility for water are some of the intermolecular forces that they make with other molecules. The weakest of these are the van der Waals forces, also known as London dispersion forces, and they're caused by temporary induced dipoles. So these temporary dipoles that create these small changes in partial positive and negative charge between the different types of hydrocarbons typically. So we're looking at carbon and hydrogen and those temporary induction of changes here. Those are the weakest forces, but they can add up when you get a lot of them lined up the right way. Next, we have dipole-dipole, where we have those sustained and permanent dipoles between less electronegative elements and more electronegative elements, like something that's attached to carbon and an oxygen, for example. We have a disparity in how these things share these electrons in the bonds, and then we get these permanently set up dipoles. And this is the next strongest. A third, we have hydrogen bonding, and it's a type of dipole-dipole. So we've oxygen pulling electrons away from this hydrogen, and we get a partial positive and partial negative charges. And it's any time that we have a hydrogen that's involved in this dipole-dipole bond, and it's a little bit stronger than just a normal dipole-dipole that doesn't include a hydrogen. And finally, we have ion-ion bonds. So if we have full total negative charges and full positive charges, this is one of the strongest intermolecular forces that is not a covalent bond. These are strong, and this is kind of the order from strongest on the right to the weakest on the left in terms of how they contribute to these things sticking to each other. So the stickier they are, the more interactions they have, the stronger those interactions, the harder they are to pull apart and boil, for example, or boil from each other, or the better that they dissolve within waters that have similar types of intermolecular force interactions, for example. So sodium chloride is a good example of strong electrostatic interactions or ion-ion interactions. So these they aren't sharing electrons, but they can be associated with each other very closely because they have full positive and negative charges. Van der Waals are, again, temporary induced dipoles, and there's just small changes of fluctuation of electrons as they move around, and what adjacent atoms will also, or molecules will also do that same thing, and they'll be able to kind of put these orbitals together a little closer and create these interactions. And we can see that this is actually what happens on the feet of different types of lizards or chameleons. They have these fat pads that are long chains of hydrocarbons that they all add up. So when we get longer and longer chains, we actually can get more of these van der Waals interactions interacting, and that can create a higher melting point because of the surface area and those interactions. When we're talking about dipole-dipole interactions, it's based on electronegativity. So anytime that we are going to be interacting these things in a comparison with those diagonal lines that I showed you a little while ago, anytime we're bonding things on the different lines, then we're going to have electronegativity differences. So here we're looking at oxygen and carbon. Between this carbon here and the oxygen, and we're going to have the electrons flowing towards the oxygen away from the carbon. So we're going to have a partial positive and a partial negative. You can see those here, and this is a kind of nice little heat maps to show you where those electrons are. We have a higher density of electronegativity in that front end by that oxygen, and then on the back end it's more blue, so there's less electron density. And then we can kind of line these up, and these will be associated with each other as we get these dipole-dipole interactions, which makes these a little bit sticky to each other. They're kind of like little magnets, and so that will help bring those together. And then when we want to boil it or heat it up, it takes a little more energy because we have to break apart those intermolecular force bonds. So a stronger intermolecular force bond that's a dipole-dipole are these hydrogen bonds. And the rationale and the reasoning for that is, think about if we have electrons being pulled away from a hydrogen typically just by itself has one proton and one electron. If we're pulling this electron away to donate it more towards an oxygen, this is almost a completely bare proton. That makes it very enticing for negative charge to be attracted towards it because it's essentially a proton that's unshielded, and so there'll be a really large attractive force. And those hydrogen bondings are quite a bit stronger than just a normal dipole-dipole because of that bare proton when we're talking about hydrogens. So these can be involved in, this is a special type of dipole-dipole that just has a little bit more strength to it. So again, looking at these, the weakest van der Waals on the top, then we have dipole-dipoles, and then we talk about hydrogen bonding, which is a strong intermolecular force, but even stronger is when they're full positive and full negative charges being attracted to each other. So just some examples of that. And this is going to change some of the physical properties. And let's look at that for a second here. If we're looking at some of the intermolecular forces and physical properties of pentane, for example, which is just a hydrocarbon, we are looking at 36 degrees Celsius. All of a sudden, we add oxygen here that's doubly bonded to the carbon below, and we move up to 76. So now we're adding the dipole-dipole bonds here. So we go from just van der Waals, and then we've added dipole-dipoles, and we've increased the boiling point from 36 to 76, so about 40 degrees Celsius. Then we can increase the boiling point even more by, instead of adding just the double bonded oxygen, a single bonded oxygen with hydrogen, which allows us to then have hydrogen bonding associated with it. That increases the temperature another about 30 degrees Celsius, and that's going to be the much higher boiling point. So butanol versus butanal versus pentane, which has a similar size molecular weight wise, but they're increasing the boiling point or the melting point for that compound. Something else to note is that if these interactions between the elements are different than what water is going to do, so water is going to generally be involved in hydrogen bonding to itself because it has an oxygen and hydrogen associated with it. So they'll be able to, these interactions will be able to kind of work and form different intermolecular forces between different water molecules. Now, if our solute that's in our solution is going to act like the solvent, in this case water, if it's able to make similarly strong intermolecular forces like as water can, it'll be able to be dissolved into water. So here's an example of different water. If we're going to have ion interactions, we can dissolve. For example, in chapter 9, we looked at some of the differences in solubility of things. So the difference in how these interact with each other or how they interact with the solvent, that's going to change if they're dissolved or not. So here, if we have full ions, typically those are going to be able to dissolve and be allowed to be dissolved into water. Butane, for example, if we have a methyl tetrachloride, we have 4 chloride groups and a carbon group in the middle. These are going to have some electronegativity differences, so we'll have partial negative charges on the outside, but we're going to have some polar bonds, but there's not a dipole there. So this is typically, the butane will be able to be soluble in this compound, but with water, because there are hydrogen bonds here that are going to be associated with it, then water is actually not going to be a good solvent for butane because the butane doesn't have any hydrogen bonding capacity between just its hydrocarbons. Acetone, now, we can actually be soluble in both because we can have the dipole interactions that will allow it to still be associated with, it'll be able to kind of organize those units so that the partial positive carbon can be lined up with the chlorine here, and then we can stabilize that interaction to make it soluble. And we can also then interact those different groups. If we have the partially negative, partially positive form here, then the oxygen in the water is going to be able to interact with that partial positive, and a hydrogen on water is going to be able to interact with that partial negative. So this allows it to be soluble in both different types of substances. The rule of thumb for something to be soluble in water usually has to have at least one polar group that's capable of hydrogen bonding for every 5 carbons. So if we have an ethanol, we have 2 carbons here and 1 polar group. So that's going to be water soluble. It would be predicted to be water soluble. This is the structure of cholesterol. There's a lot of carbons here, and we just have 1 polar group on the end. So certainly not a 1:5 ratio here. And this is, cholesterol is insoluble in water. So now we've had a chance to go through some of the properties of alcohols, and we're going to get back to that a little bit later as well. But I do want to discuss some of the differences in terms of naming. How do we, the nomenclature or naming of alcohols. So there are a couple different rules that we're going to focus on. And one is the first thing is we need to find the longest chain. When we find the longest chain, it's the same type of naming that we looked at before when we were looking at alkanes. We're just looking for the longest chain, and we can just count the same way that we did with the alkanes. So we can say methyl, ethyl, propyl, butyl. So this is the longest chain, and we can number it however we want. But we also have to make sure that when we're counting the longest chain, our functional group now, our alcohol, has to be associated with that longest chain. Number one, we have the longest chain. And the kind of second rule is that we want that functional group to have the lowest number. So it's attached to the lowest numbered carbon. So we have 1, 2, 3, 4. We have it on the 2 instead of, if we counted it from backwards, 1, 2, 3, and 4, that number is a 2 going from left to right, and it'd be a 3 if we counted from right to left. So the 2 is the lower number, so that's the number we would want to use. Here, so we have the methyl, ethyl, propyl, butyl, so that's a butane base group. The alcohol is on the 2 compound, the 2 carbon, so it's the 2-butane. We take off the E ending and add an OL ending. Also off of the group here, this second carbon, we have a methyl group, so that is the 2-methyl 2-butanol. So instead now with this functional group, instead of, for example, when we were looking at double bonds, butene, we'll just take the base of that word and then add the OL ending. So butane all. So take off the E, add the OL ending. All right, so let's look at this next example. So here we can number 1, 2, 3, 4, 5, 6. So we have methyl, ethyl, propyl, butyl, pentyl, octyl. So that 6, though, we want that to be the lowest number possible, right? So we're going to have to switch the numbers around so that we can keep up with our longest chain, and then have the functional group with the lowest number. So we're going to have to number it from right to left instead. And we have on the 1 carbon is our alcohol, so that's the 1 and the OL ending, hexanol. So that's methyl, ethyl, propyl, butyl, pentyl, hexyl. That's where we get that base word. So it's 1 hexanol, but then we have 2 substituent groups that are attached to the 5 and 3 carbons. So 3, 5, and then we get a dash dimethyl because there are 2 of these. That's the di, and then dimethyl 1-hexanol. All right, let's look at this last example. We can number it from both different ways, but I can see the alcohol is more on the right, so I'm going to start numbering it from right to left. So we'll do 1, 2, 3, 4, 5, 6, 7, which means that we're going to be at hept. Hept is the kind of base word there. On that 3 carbon, we have the alcohol functional group, so 3-heptanol. And we also have a substituent group on the number 6 carbon. So we have that, and that's a methyl group. So 6-methyl 3-heptanol. So there's some examples of naming these types of compounds. So I'd like to go through a few different examples with you. And for this one, we have to start with typically we have different priorities, and I'm not going to get too much into detail here with these. I wouldn't worry too much about this, but we have 1, 2, 3, 4, 5. So we know that the 5 is the pentane would be kind of the base word. Pentane for the 5 carbons. Typically we have different priorities. So a higher priority here is we're going to name this as an alcohol because we have an alcohol functional group over a halogen, for example, either of these. And between bromine and chlorine, we're going to name it, the bromine is heavier, has a higher molecular weight. So typically that has a priority over the chlorine. So we name this a 1 carbon here because it's got the higher priority group. Then we go 2, 3, 4, 5. Now what I noticed in the book is actually it's named, this is from the book, we have a 2,4-chlorocyclopentanol. I believe that's an error in your book. This should be a 5 because we go from the 1 carbon, we count over to the higher priority group, and we're able to get the 2-bromo-5-chlorocyclopentanol. So that is how we could name that, that compound. Apologies for that error in the book. When we're looking at these other kind of two, what we have to notice is that we actually have 2 of the same functional group in one and 3 in the other. And so it doesn't matter in this instance which way we number it. We can just do 1 and 2. We can do 1, 2, and 3. And we're going to have that methyl ethyl group. So that's the F, that's kind of the backbone there. And then we have the prop from propanol for that second compound. And you'll notice we have a diol and a triol. So that's the difference. If we have 2 of these, we have a di. If we have 3 of these, we have the tri. So we have to still number them based off of 1, 2. They're attached right next to each other on the chain, 1 and 2 ethanediol. And then we have the 1, 2, 3 propanetriol. So that is kind of a different rule if we have multiple functional groups on our compound of interest. So these different alcohols with different names, like 1,2,1-butanol, for example, versus 1,4-butanediol with 1 or 2 of these alcohol groups, we're going to see that as we get longer, we will increase the boiling point. But as we also if we add another alcohol group, that's going to change the boiling point considerably as well. So look at 1-butanol, where we have a boiling point of about 117 degrees Celsius, versus 1,4-butanediol, which has the 2 alcohol groups on it. And we can raise the boiling point by 200 to 230 degrees. So it almost doubles that boiling point and allows it to be soluble in water, where we have 1, 2, 3, 4. It's a slight solubility, but it increases substantially the solubility once we've added that other functional group. So something to look at in terms of the properties and those different compounds based off of their name. And when we're looking at these, it really depends on the shape and those intermolecular forces we spoke about in terms of the boiling point. So these are going to have a lot of influence on how these things are going to interact, and the density kind of that positive and negative charge is going to dictate that boiling point. You can see we have a dark blue and a dark red telling us that we have a higher and lower density of electrons. This allows intermolecular forces for interaction. And here we can see that if we look at these different functional groups, if we have just a normal propane with similar molecular weights for all of these elements between these 3, we have propane that has a boiling point of negative 42 degrees Celsius. We add that oxygen in there to give it the dipole interactions, and we go up to 23, and then we make it an alcohol. Then we have the boiling point at 78.5 degrees Celsius. So a substantial increase by allowing for between dipole-dipole and hydrogen bonding. The next section we're going to kind of discuss, now that we've discussed how to name these things and some of the general properties of alcohols, we're going to talk about the different types of chemical reactions that we can undergo with alcohols, and then some of the different types of oxygen-based compounds.